We're all incredibly excited about today's call because we've got Tess, who's going to talk about this this seminal FaceNet paper, which I think is probably one of the most kind of impactful papers in the in the area of facial recognition. I just want to make the comment that this call is designed to be friendly. It's an inclusive atmosphere. It's anti-elitist. There is no such thing as a silly question. So please bear that in mind and enjoy the call, guys. I'll hand over to you, Tess.
Yeah, thank you, Tim. So on that note, if I say a word that you don't understand, or if I do something like too academic, because you can kind of get that way when you read papers, please do call me out on it, because I don't want to talk in a way that I wouldn't understand myself. So this is about FaceNet. It's a paper about a unified embedding for face recognition and clustering, and we'll get to know what that means. It's done by 3 guys at Google, and I'm sure a whole group behind them. And we'll see actually a theme in the next few weeks that Google has produced quite a few of these papers. But my name is Tess. I'm from Sweden, and these are the first few numbers in my face embedding. So what this paper is actually about is essentially taking a picture of a face, reducing it to 128 numbers, which essentially means a dot or a point in 128 dimensional space, and then using that number or that array to do classification of faces, like identification, verification, and clustering. So it's quite impactful because once you have that small embedding, like that small array, you can then store it in a database, for example, and with 128 bytes, you can store quite a few before you get up to a reasonable size of memory. So it's a very, very important sort of discovery. Now, I'm not going to get too much into the minutiae of the paper, but I thought it would be nice to kind of look at the abstract. And this is quite a readable paper, actually, compared to some of the other ones that are a bit more heavy on the math. But this is the abstract for the paper. And what it talks about is, despite significant recent advances, now remember this is 2015, the recent advances they're talking about here are Deep Face from Facebook and Deep ID2. It's hard to do something at scale. So we'll talk about those problems. And then we say if we present a system called FaceNet that directly learns a mapping from face images to a compact Euclidean space where distances directly correspond to a measure of face similarity. What that means is that 128 byte vector, a point in 128 dimensional space. Once this space has been produced, tasks such as face recognition, verification, and clustering can be easily implemented using standard techniques. And we'll look at sort of how to do that. And then it says our method uses a deep convolutional network trained to directly optimize the embedding itself. That network that they propose is called Google Net. It's an inception network, so we'll look at that. We use triplets of roughly aligned matching, non-matching face patches. We're going to look at what that means. Specifically, this paper brings up something called triplet loss and triplet selection, which is quite good, not only for this, but basically for all one-shot learning techniques. And the benefit is that we can do state-of-the-art face recognition using only 128 bytes per face. And that is sort of like the grunt of this, the fact that we can now store our faces as a representation of just 128 bytes. Finally, they talk about some results on this and about this data set called labeled faces in the wild. So that's a benchmark data set that's lately actually been turning out to be quite biased. So I'll mention that in a few words as well. And then they end off with talking about something called harmonic embeddings and harmonic triplet loss. I'm not going to spend too much time on that, but essentially that means that when they did version 1 of FaceNet, you could produce these embeddings, and then you can now reuse them even in combination with embeddings produced by version 2 of FaceNet and so on. So So that is the purpose of like the harmonic embeddings and triplet laws. So now that we know what we're going to talk about, let's start off with sort of the problems with old approaches. And I'm going to go back to even before deep face. So if we have a new startup, oh, sorry, I'm going to go through this first. So what we're aiming to do here is essentially doing verification. So identifying if this is actually the person we're looking at, or identifying who's in a picture, so we can sort of tag them or do things like that. Or like in this case, I've taken a lot of pictures of this one guy, figuring out, like basically clustering my images based on the people that I take the most pictures of, and then figuring out who it is, so clustering. But our problem, and the problem with previous approaches, looks a little bit like this. So we have this awesome startup with some really nice people, and now we want to create some kind of like photo verification where when you go through the door, it should automatically let you in if you're in the company. One way to do this, and kind of like the thing that maybe pops into your head, is doing classification, like standard classification. So it will let me in because I'm one of these 6 classes, I'm Tess, but it wouldn't let this guy in because he's unknown. Now, while that's easy and that's sort of how we always do image and image work, it doesn't really work at scale, because what if our company isn't a startup? What if our company is Microsoft and we have like 100,000 people? Then we have 100,000 classes in our classification, which obviously wouldn't really be a good thing. And you know, the more classes you have, the more images you would have to have. So since not everyone takes as many selfies as Tim, we have a bit of a problem. In fact, Jana doesn't take many selfies at all, what I can tell, so she wouldn't be classified very well. And the third problem, maybe the most irritating for us as data scientists, is that what if this guy joins the company? What do we have to do? Retrain the network. That's not really workable in a situation.
If he joins, we have to celebrate.
So what? Yeah, exactly. We do have to celebrate. We would retrain the network specifically for this guy, I think. Now, so if we can't use this type of technique, we have to use something else. And this was kind of like one of those aha moments for me in machine learning, because CY was talking about a problem where they wanted to see if a specific garment that came in was actually part of a product catalog. And they only had one picture of each element in this product catalog. And she asked, okay, so if we're in this situation, what can we do? And at that time, I knew linear regression, and I knew it wasn't that. And I knew logistic regression, and I knew it wasn't that, because she said classification was sort of out of the window. So I was like, how about like we do some type of like clustering, like put similar things together? She was like, okay, can you explain some more? And I was like, no, that's the only word I know from machine learning, so I'm going to skip that. But it turns out that that is essentially what we're going to do. So little did I know then that I actually sort of figured out what we were going to do, except for I didn't figure out exactly how, and that's what we're going to talk about now. So we're going to learn a similarity function. We're going to, instead of like actually doing classification, we're going to try to figure out how similar things are, like how similar these faces are, and if they're similar enough, we're going to identify them as true. So in order to do that, we need to figure out these 128 byte embeddings. And embeddings, if you don't know what embeddings are sort of like the core of what deep learning is all about, finding a semantic meaning, like finding an actual meaningful way of describing things. So if we look at words, for example, and this is sort of a preview of Tim's paper next week, Word to Vec. If you have 3 words and you don't know English, so you're like a machine learning algorithm, you might think that peach and beach are quite similar. In fact, probably a lot more similar than apricot and peach. But we as humans know that anytime you can use an apricot, you can pretty much use a peach too. Like most people probably wouldn't even know the difference between apricot and peach. You can make jam of them. You can have all these sort of meaningful things about peaches and apricots, like their color, their taste, and so on. And you know also very well that beach is a very different thing. You can't make like beach jam. So if we, instead of the words, could capture these meanings, that would be really useful. And that is what embeddings are for. So if we take an example of movie recommendations, and we have all these movies, and someone liked Shrek, and now we're going to recommend another movie, then one way to do this is sort them in a meaningful way. So in this case, sorting them from child movies to adult movies, or maybe even giving them a few more dimensions, like if it's blockbuster or not, and how about giving them another dimension, like is it an action movie? How many times does Brad Pitt show up? All that kind of stuff. And the more meaning you give, the more dimensions you give to this. The cool thing about this is once you've given all these dimensions, you can now plot them in space. So in this two-dimensional space, they have coordinates. Coordinates that you should be used to, like from grade school math, or from like elementary school math. And the even cooler thing about this is that we can now say that the more similar these are, the more closer they are, the more similar they're going to be. So if we can measure the distance between two things, we can also tell how similar they are. So Harry Potter, if someone likes Harry Potter, what other movies would they like? Probably maybe Star Wars, but they might not be like so interested in this Waking Life movie. And the more dimensions you give them, the more sort of similar, the more the clustering makes sense. So how do we get embeddings from images? Like this, right? We get one of these dense layers, or one of these fully connected layers, flat layers, and that is our embedding. Now, if we were to cluster images, so this is a data set, and this is that label faces in the wild data set. So I picked out like 13 people or 10 people, I think, and I cluster them, and we see that they cluster quite nicely. So this is a t-SNE representation of this. Normally they're in 128 dimensional space, but t-SNE kind of like compacts it into 2 dimensions so we can plot it. And now we can see that here are the guys in the data set. So Bill Gates up here, we have Tim here. We actually have like one Bill Gates image that kind of clusters into Tim, and we also see that Tim is
very similar to David Beckham.
Yeah. Happy about that, right?
If only.
Right. And then we have the women, and this is quite interesting actually, because when I do this howoldareyu.net, sometimes I get mistaken for a man. And it's probably because of this, because compared to all these other women, my face is has more male features than the rest, sort of. Now, this is a quite limited data set. Now, we have a couple of outliers in here, Venus and Serena Williams, and they cluster very closely together, and as we'll see later on, they're often misclassified for each other. This is actually a little problem in this data set because it's heavily biased towards male, and it's heavily biased towards white. So, and this is the benchmark data set. Now, cool thing though is that this clustering actually seems to make some sense even in the face world. So the distance is just a regular distance that you would calculate in like Cartesian space. Not actually 100% sure what the difference is between Euclidean and Cartesian space, but just calculated like you would have in math. And this distance is called the L2 norm, and it's mathematically displayed like this. And I only point that out because in documentation we'll see this notation quite a bit. The distance is then further placed on something called the unit hypersphere, which means that like from the center you have a distance of 1. And they do this sort of like to scale the distances. And a distance of 0 means it's an identical picture, and a distance of 4 is basically as different as it can be, but it's sort of a scale that goes like this. So if you're between 0 and 1, you're pretty darn similar, actually. So once we have these embeddings, how do we use them to solve face tasks? Well, it turns out it becomes quite easy, because if you want to do verification, is this me? Yes. Then you can just look at the distance threshold. So you take the picture, distance of the ground truth of me, and a new picture of me. And if it's like lower than a certain threshold, maybe 0.7 or something like that, then it is considered to be me. If you want to do identification, then what you do is you look at the items in your database, like all these people that you have in the database, and you look for the lowest distance, or you do a KNN or SVM classification. So for me, the lowest distance here would be this, so it would identify me as Tess. And for Anders, the lowest distance would be Chris, but it's above a threshold. Now we will have to set a threshold for this, but it would be above a threshold, so it wouldn't actually be calculating it as Chris, and so it will be calculating as unknown. And finally, clustering is just a matter of like finding, like doing k-means clustering or something. And we were discussing this earlier about, because one of the problems with k-means is of course that you will have to tell how many clusters you have. But because we know what a good distance measure is, we can actually do some trials and errors and figure out like that the clusters are actually nicely clustered with a distance separating them. So that was sort of like the problems and the embeddings. Now they said recent advances. So recent advances turn out to be deep phase, for example. So deep phase also used the similarity function. It had something called a Siamese network. So basically a network that has shared weights. It was also calculating embeddings. It wasn't actually calculating 128 byte embeddings, but it was doing it by doing classification. So you sent in 2 pictures of someone that was the same, it classified them as 1. 2 pictures that were different, classified them as 0. So it was concentrating on this calculation or in this classification task, and this embedding was sort of the afterthought or like the byproduct of this. The difference between this and this paper, the FaceNet paper, is that the FaceNet paper actually concentrates on the embedding and actually uses the embedding in the loss function instead of the classification. So that's what they mean about, and that's what I meant with that in the abstract.
Tess, can we just quickly point out on Siamese networks that the weights are shared? So yeah. the Siamese bit means that these are copies of each other. When you do the weight update, it's actually the same object in memory.
Yeah, that's very important. So in fact, we'll get into that a little bit later, actually. So but yeah, essentially you just have like one stream that you go through. So how do they concentrate on the embeddings? Well, they use something called triplet loss and triplet selection. So triplet loss works a little bit like this. I have a picture of me, that's the anchor, that's sort of like the ground truth. And then we have a picture of also me, so this is a positive. And then we have a picture of someone who's not me, a negative. So you have 3 pictures, anchor, positive, and negative. And the goal of this is to make sure that the anchor to negative is always further away than the anchor to positive. So there's a shortened distance between me and the positive, and then between me and the negative. So in math terms, it looks like this. If we move it to the other side, we see distance anchored to positive minus distance anchored to negative should be less than or equal to 0. Now, this is quite easy to satisfy. Let you think about that just for a second, how you would satisfy that. So one way that
pick easy combinations.
Yeah, so what's the easy combination? Like what would satisfy this quite easily? Like if you would just sort of like as a baseline just enter some numbers, what would be easy numbers? Maybe that's a very hard question. If the distances are always 0, so if all the vectors, if all the embeddings are the same, you would always satisfy this, correct?
Yeah.
So essentially, if all the vectors start at 0, or if all the vectors start at the same random number, we will always start the same. So that's a bad thing. So in order to fix that, we, sorry, this is the math notation. In order to fix that, we add a margin. So we have to say, not only do they need to be like, not only the anchor to positive need to be like less than the anchor to negative, but it has to be a lot less. Like we have to stretch it out by a margin. So something like this, where this distance is 0.3 and this distance is 0.32, is no good. If the distance margin is 0.2. So 0.2 was what they suggested in the paper. So this is sort of like the essence of the paper, finding this triplet loss. And if we go through and say, okay, so we, this is the triplet loss again. The cost function looks like this. So the cost function is then the sum of all the distances. This plus sign here just means like a max of 0 and the distance. So we're only looking at negative distances, or sorry, where the anchor to positive is less than the anchor to negative. And as you said, Chris, finding the right triplets and finding like those that are very similar actually is a very good way to get this to converge fast. So we need triplets that violate this equation. So we don't need triplets where it's easy to find the differences. Instead, we need triplets where the anchor to positive are actually very different. Like so, the positive images should be very different, and the anchor to negative should be as close together as possible. So this is a hard triplet where the we try to maximize the anchor to positive and minimize the anchor to negative. We do this because if we would just pick easy triplets like me and a picture of me taken yesterday, and then compare that to maybe a person with Indian heritage, that would be very easy for the system to sort of differentiate. Whereas me and a picture of me taken 10 years ago, and then me and a picture of my sister, that would be a good triplet. And this argmax and argmin is a way to find those triplets. Now, so they talked about a novel way of finding these triplets. So they came up with 2 ways of doing this. So either you could generate them offline, so outside of the training mechanism, every n steps from a subset of the data, or what they actually settled on was generating the triplets online while actually training. So every time you start with a new mini batch, you do this argmin and argmax. And they use this with mini batches of 1,000 or more. But the reason why they don't do it on like the full set of data is because if they would do it on a full set of data, you would sort of always pick mislabeled images, because mislabeled images for positives would have a large distance, and mislabeled images for negatives would have a small difference. So that's why you don't want to do that with a full set. Does that make sense? Hopefully.
Yeah.
Yeah. So the CNN architecture, we have our batch coming in, we have a deep architecture. I'll talk about that in a little bit. We do an L2 normalization. This is done to put it on the hypersphere. And then we get the embeddings and we send it into triplet loss. So it looks like this. We have 3 CNNs, or in essence, 1 CNN, because it's a Siamese network with shared weights, like Tim was pointing out. It then outputs the embeddings for the anchor, for the positive, and for the negative. So it's always going to use like the same network to generate these. We get into this triplet loss, which basically calculates the difference between the anchor positive and the anchor negative and tries to minimize that. And then it propagates back to this. So the Siamese networks usually are done in pairs, and this is the first time sort of, I think I've seen it in threes. But it's a pretty common structure for doing similarity functions in general, even if you don't use triplet loss.
Just a quick point there, Tess. In the paper, they did actually say that they didn't directly compare this method to the standard Siamese network. So we don't know for sure that this is better, but presumably it is better.
Yeah, so exactly. So they were talking about the intuition why this triplet loss was better than, for example, what FaceNet was using, or for what DeepBase was using. And when you do classification, what their point was that your embeddings, like the byproduct, like the embeddings that were generated during the classification, would be focused to one single point in space, where with this, each image can sort of get their own dot, but they're clustered together and they're neatly clustered together. So it gives them a little bit more flexibility. I don't fully understand how that works, but that is sort of the reasoning why they thought this might be better. So this is how it looks when it comes in. So 3 inputs into one model. So this is the Siamese network, concatenate them, and then as an output, you now get like all these 3 embeddings in one array, and that's then sent into the loss. They looked at a couple of different networks. So one is Saylor-Fergus, that's a fairly standard convolutional neural network, and then a few inceptions and some mini inceptions. So they settled on an inception network, this NN2, that gave the best results. And an inception network, I want to say this is Google Linnet. So Linnet is a very, very old network architecture. So that's sort of a nod back to that. But
Tess, just quickly. So there are some quite big differences in performance between those architectures. Yes. Was that mainly a function of the architecture or the input size?
Are you talking about like these?
Yeah, so so they've got different input sizes. So the 220 squared seems to work well.
Let's actually see. Like, so they were talking about input sizes, I guess. No, this was the quality. I don't know actually. I didn't look into that, but they said they were getting quite good results even with like fairly small input sizes. So but yeah. I know, for example, the one that I'm using to test and the open source implementation of this uses NN small 4, which is a smaller version of this inception, so much less complex one. I can't really say.
Okay.
Do you know? Or no?
It seems to be related to the size of the network based on what I've read.
It's a bit of both. So when I read it, they were talking about the fact that between NN1 and NN2, so the inception net has far fewer free parameters.
Right.
But but it requires a similar amount of flops to train, probably because it's a more complex architecture.
Yeah, so
but
performance.
I don't know the nitty gritty.
Yeah. So they very much talked about the performance as far as like how many and like how much computing power it would require, but this performance, I'm not sure that they talked about that too much.
Could we just quickly define what this validation rate is?
Yeah, so this is sort of like the precision. So how much, like how many of the true positives were labeled as true, right? Let me see.
Yeah, I think it's the true accepts normalized by the number of people that are the same.
Yeah. Because they had like the definition of this val. So val is true accepts divided by p same. So basically by the real truth. So that is like the precision.
Yeah, so all face pairs I and J of the same identity are denoted as P same.
So out of all the people, like how many people did it? Out of all the people that were Tess, how many of those were classified as Tess?
Yeah, sounds about right.
Because they also have this far, which is basically false except p diff, like so recall, I believe. This is sort of the it looks like this is the standard for all of these papers as far as what they use as the performance measure.
Yeah, that makes sense because then they plot it on a kind of rock style curve, don't they?
Yes.
Yeah. Okay, let's not get bogged down. Let's move on. But I just want to encourage everyone to ask questions and stuff. This isn't a lecture. This is an interactive kind of session. So do jump.
Absolutely. So inception, if you haven't seen that before, inception is when you can't really figure out, should I use like 3x3 or 5x5 or 1x1, use everything and let the network figure out which one to use. And that's like my 1 minute spiel about inception. What they did find though is that they could safely remove the 5x5s. They were almost never used without losing too much precision in this case. So the data sets and the results. So as we've seen, the inception was the one that they used. They used 26, or in fact, 260 million at some point images. Now, one interesting piece about this is when you start thinking about how do they get these 26 or 260 million faces. This is Google, so they have access to a lot of data. But one problem when you create these data sets is that you normally use face detection to get like sharp crops. And face detection is known to not, or has later at least been known to not actually identify very dark skinned faces very well. So using these techniques of face detection means that you will always have a very, very biased data set. A data set is heavily biased towards lighter skinned people. So that is a little bit troubling. They looked at some, the quality didn't seem to be extremely important. And they went through and looked at how big the embeddings should be, because one of the problems that they had before as well with deepface, for example, is that the embeddings would be sort of like 1,000 bytes, and this is now a way to kind of bring it down to 128 bytes, which is quite nice, and they were getting very good results with 128. In fact, they were saying you could probably get the same results with a larger one, but you would have to train it longer and train it with more data. I want to mention this benchmark dataset. So this benchmark dataset is called Labeled Faces in the Wild. So you can just download it as an open source dataset with 13,000 images. So this is sort of like what all these are tested on. Now, lately it's been known. So this is in 2018, this guy from Microsoft and this girl, Joy Bulwian, I can't pronounce her last name, and did some research on this and found that it's basically 77.5% male and 83.5 white. That particular number came from Hanning in 2014. So the benchmarks are biased in themselves. She did, so this is Joy, and she does all her research with a white mask because most of the face detection can't even detect her face. But she then discovered that basically gender checking, even Microsoft's face detection and face identification, like it has a 1% error rate for light-skinned males and a 25% error rate in dark-skinned females. So this is actually a current stream of research in the face recognition area. Basically, how can we debias these data sets? How can we get face detection to be better? And based on that, I also added a few more people, and it's quite interesting because this split that we saw here doesn't necessarily apply to Tiger Woods. He's very intertangled with Serena and Venus. I also put in Jackie Chan. I had to pick these people because if you look at the data set, like there are very, very few people that you could even pick from Asia or from like with darker skin. So a couple of other notes. Now this paper, and we've been debating this a lot, me and Tim, about the alignment, because the paper quite specifically states that it's pose invariant and illumination invariant, which it is if you have like tons and tons and tons of pictures. However, if you don't have tons and tons and tons of pictures, it's quite nice to do alignment, and there are some pretty good alignment software or alignment packages nowadays. So typical alignment for example, OpenFace, which is an open source implementation of this, is that you take the picture, you get the landmarks, and you switch it up like that. So with that, I would get these pictures of myself.
Just to be clear, Tess.
Yeah.
Presumably, so Google have trained this amazing model because it's been trained on 26 million faces, and their training data kind of, randomizes across all of these different poses to a reasonable degree. Therefore, it's pose invariant. But that model is not publicly available. If we want to use this FaceNet ourselves, we can only train it on publicly available data sets, and therefore we'll need to frontalize the image because we'll lose that diversity.
Yes. So in the paper, they state that they crop. So they do some kind of face detection using Picasso, for example.
I think the reason for that, though, is because their input size is so small. If it's only 96 pixels squared, they would reasonably kind of, crop the training.
Yeah.
But it would still then be invariant to pose. I guess the reason I'm bringing this up is that the promise of deep learning is that in an ideal world, you don't need to do feature extraction at all. You can just pass in the raw pixels. Similar thing with sound processing. In the olden days, you would have to do a Fourier transform and do some feature transformation. And these days, given enough data, you can just pass the audio data, the waveform domain in directly. And it's one of these things, isn't it, that if you have enough data, it just does everything for you. Because in FaceNet, it was learning a kind of a set of kind of points on the face, wasn't it? It was learning an
like
intermediate
in deep face, you're talking about.
in deep face, yeah.
Yeah. Yes. Yeah, totally agree. So yeah, in theory, we shouldn't need this. In practice, we kind of do because of the data sets that the open ones have been trained on.
Do you know how many faces our cognitive services API was trained on?
No, I have no clue.
That'd be interesting to know, because just as an aside as well, I think recently we announced news that our cognitive services face API is not racially biased, or it is less racially biased. I'm not sure exactly what the details are. Maybe someone else can comment on that.
Yeah, so I mean, so this one, let's see, where did I put this? No, here. So this research was, so Timnit is one of the people in the FAIR AI. So we have a fairness in AI research group in New York. And this research was actually done on the cognitive services as well. So cognitive services was one of the ones that had like this high problem space. But it was only because like all of them had it. So I guess based on that, they took action on that and sort of debiased the data set, perhaps. I guess that was the outcome of this, because this is quite recent. This is from 2018, actually. Okay, so any questions on this? I was thinking I was just going to quickly go through.
This is Omri.
Yeah.
Can you hear me?
Yes, I can.
Maybe I missed it. So you mentioned face detection. Did they mention how they did face detection? Is it a part of the architecture, or did they use some other technique as a pre-process?
They mentioned that they used Picasa to crop the images. So I guess they had
So
like
it's some proprietary, yeah.
Yeah.
Mm-hmm. But do you know if people still use the traditional Viola-Jones style models, or is there any new architectures for face detection?
Are you talking about like, do they still use the inception, or do they use the? Sorry,
no, just for cropping the face out of the entire picture. So there used to be a traditional method for doing this. I think it was called Viola-Jones.
Okay.
I'm just wondering if it was pre-deep learning, so I was just wondering if there are new approaches for just doing the object detection specifically for faces.
Yeah, so I'll show you here. So this is a notebook for basically using OpenFace. So this is sort of what the inception model looks like if you look at it. I'll get to your question, Omri, like, because it's further down in this. But this is the inception model, so you can see it's quite large, even though this is a small version of the inception module. This is how the triplet loss is then calculated with the p distance, like positive minus negative distance plus the margin. In this case,
and just taking a quick pause here, isn't it mind-blowing how simple this is? So the entire thing that we've just been talking about is right on your screen. That's it.
Yeah.
That is it. You know, other than there's this small, you know, go and get me a CNN encoder, but we all know about CNN encoders. I mean, that's it right there, guys.
It's this in 260 million images.
Yeah, exactly.
Oh yes, and that.
It's a little harder to.
Therein lies the problem. But you have these inputs, you then have this triplet loss layer. You combine the inputs and the triplet loss layer, and that is your model. So your model looks like this. Inputs, same model, triplet loss layer.
So
and
cool.
then, yeah, and then you have this generator, which is actually, in this case, it's not implemented, it's just a fake. But that would go through and pick those very different triplets for you to make this converge faster. But then using a pre-trained model, and like the open face model, we can do this. Like basically we can just generate these embeddings. And I wanted to get down to this is how the alignment is done for this particular one. So this is using also a pre-trained model that's pre-trained on finding like these 128, or not, forget about 128, pre-trained on finding like a large number of dots in your face, like what I was showing in the last slide, where it was finding like the corners of the eyes, the nose, and things like that. And in this case, what we're saying is we're going to concentrate on the outer eyes and nose, here and here, and put those in specific places in the picture. So the eye should go here, the nose should go here. Does that answer your question? Or was that even what your question was about, Omri?
Maybe it does. I'm not sure if the alignment and landmarks placement actually help with. Yeah, I guess it does. So they're using landmarks, a pre-trained landmarks model. I'm just trying to make sure.
It is using a pre-trained landmarks model, and it's using this dlib, which is a module that you can use. You pass in what the landmarks are, like what the landmark model is, and then you extract sort of parts. Like what this will do is it will produce from the picture, it will produce a number of landmarks, which I think maybe we have 200 or something in our face. Like if I go back to this one, all of these numbers.
But yeah, it's just quite interesting, isn't it, that the less data you have, the more feature transformation you need. Because, you know, presumably in an ideal world, if we had infinite amounts of data and compute power, we wouldn't even need to, you know, to find where the face is in the image. We could just pass in entire images, and it would learn, you know, where the face was, and it would learn how to, you know, transform the face and to turn the face into an embedding.
If we had infinite amounts of compute power and data, we wouldn't even bother training a model. We'd just look it up directly in the infinite amounts of data using the infinite amounts of compute power. Sorry.
Wow, that was a nice digression into the philosophical question.
Right. So,
but just another point, because I'm sure Tess already spoke about this, but so Google trained the main model on 26 million images. And this is an example, because in deep learning, if you have millions more data points, the results do actually get better. And I think the difference between 2 million images and 26 million images was still quite significant. It was still about 10%. But I think the implication is that if you frontalized the data, you could even train a model on this LFW data set with 13,000 images. So you could train a model on that, but it wouldn't be anywhere near as good as Google's one.
So this particular data set that they trained the open face on is also a public one, but it had, if I recall, 500,000 images. Because I should say the LFW data set, so if we look at how that looks, this is like this looks like this. You have a number of folders and a number of pictures in them. And there are like 256 pictures of Donald Rumsfeld. So that's just one person who's taking up like a large amount of this data set. And then most people, we only have like one picture of. So this data set in itself is quite weird. In fact, only 158 people have more than 10 pictures. These are the people that have more than 10 pictures. And just taking a quick stroll through them, we'll look and see. I mean, they're very much men with white faces. So once we have the pictures and we have this model for generating the embeddings, we then used to basically extract the embeddings and save them away. And now we can go through and create distances. So the distance, we already know how to calculate that. And for example, here's a picture of me and me. So that's 0.17 difference. And a picture of me and Tim is like 2 away. So I mentioned the threshold for when we would say that a picture would actually be like the same person. And we can go through and say, you know, what threshold, at what threshold do we get what accuracy? So we go through a number of thresholds and see how accurate are we in terms of like guessing the exact right person. And it turns out that at 0.71, we get like a 96.4% accuracy in this very limited data set of 13 people that I have. So that will be my threshold for this. And here we'll look at some distributions. So basically, for distances for positive, we have most of the distances are lower than that. Distances for negative, most of the distances are higher than that. We have a few that will fail in here. And then for this one, I could have just done like quick search, like so in, like I showed in the PowerPoint, but I did like a KNN and an SVM classifier, because a KNN classifier is essentially doing the quick search.
Does anyone know a nice, efficient way to be able to do this in a database? You know, so like are there database indexes that can do these distance similarity resolutions?
I'm sure you could, like, because if you store a mass, like the separate numbers in separate columns, it would be quite easy to create.
Yeah, because I think if you did a search, it would be, you know, it would have an O of n time complexity, a linear time complexity. So it stands to reason that you would take it out of the database and have all of the vectors in memory.
Yeah.
But probably what you could do is kind of create a tree search. So you create, you know, clusters or recursive parents of average points, and then you kind of search down the tree, and that would give you a like a log of n time complexity. But I think in all cases you would probably want to do it in memory.
Do it in memory, yeah.
Because we know sort of where they are in space, right? So we can quite easily say, okay, so we're only going to look at, like, if we were in 2-dimensional space and we said, okay, so I'm in this quadrant, we would only need to look at this quadrant. And even we can like separate it down into much, much smaller pieces that we would search through. So we don't actually have to calculate for all of them, because we already know where in space they are. Like we could have like a hierarchy.
That's the intuition behind KD trees and quad trees that are usually used for such a search.
Yeah.
Exactly what you said.
Yeah, exactly.
So I went through and I just did a classifier for each, and you can see all my pictures of me were classified as me. In this case, dlib will only take like the biggest face and like the most front-facing face. So this is who it picked out. For Tim, it also picked him out as him. But if we look at the misclassified images, we'll notice that this gentleman is recognized as Tim Scarp.
Yeah, I've got Microsoft in my DNA.
Yeah, for sure. And please don't forget Sandra Bullock.
Yeah, absolutely.
But also Serena and Venus are misclassified as each other. And here is the Tisney visualization. So with that, I'll leave.
Well, we have 5 minutes left. So any other quick questions, and then I'll round out the call. No, I think that's it. Basically, Tess, I just wanted to say this has been amazing. I mean, you have just taken this to such an incredible level. You could have done this talk at any, you know, large conference and it would have gone down brilliantly. I can't believe that you've gone to this, you know, level of excellence for a weekly call. So thank you so much. Well, no, it's been brilliant for all of us because you know, I've certainly learned a hell of a lot just you know, speaking with you on this, and I know the wider group will benefit because facial detection comes up in so much of our work, and this is really, really important. So thank you so much, Tess, and I know many more people.
Ask a question for a second, because I think you sort of have an idea on this. Like these same techniques we can use for other image searches, sort of, right?
Yeah, I don't see why you couldn't use it for all sorts of different similarity things. This is Chris. Yeah. Sorry, I know you direct that on me.
Because this, of course, like based on, you would have to still have a lot of data to start off from, but I think this is sort of like how you do image searches in general.
Yep. I can confirm the deep learning paper is actually using a triplet network as well. And the actual problem is the data set size. So that's the main problem.
So do you know how many images you need in order to be able to train?
Around, they say around tens of thousands at least. They, in the deep ranking paper, they say they've been training on millions of pictures.
Okay, cool.
But you could probably start with potentially a pre-trained model to initialize the Siamese network weights, right?
Yeah, that's something that Tess and I were speaking about, and I don't see why not.
I see why not. Yeah.
That's actually really interesting, and I'm surprised that they didn't do that, which makes me think there's a good reason. But that's an open question. Anyway, guys, we're coming up to the hour. I just want to say again, Tess, you've set the bar so high. I want to reiterate that this is not expected. This is a casual, inclusive, friendly call, and even if you haven't really prepared any slides at all, we can just have a 20-minute conversation. Please don't be intimidated by this call because I think this has really been amazing. But I don't want to intimidate other people. It's just a friendly call. But Tess, this has been amazing. Thank you so much.
Thank you.
Yeah, see you guys on the next one.
Yeah.
Thanks, Tess. Great call, everybody.
Thanks. Bye.
See you.
Bye.
Also, Olivia watched it too. Olivia, who's 8, watched it and she enjoyed it.
I'm not 8.
You're close
Hey,
to
Olivia.
8.
Bye.
See you later. Bye.